In this video, we break down a mind-bending conversation on the nature of time and space. Watch closely as we explore Einstein's famous light clock thought experiment, which demonstrates how movement through space directly warps the passage of time.
The weirdest thing that I've ever heard anybody say is that all time exists currently.
That's Einstein. I mean, that goes back 120 years.
That's such a bizarre thought.
We don't know if it's true, but Einstein really thought there wasn't much of a way around it, because he said, okay, well, if everything is going at different velocities compared to everything else, right? I mean, it's a great question a kid can ask. How fast am I going through space? You know, and the Earth, if you're on the equator of the Earth, that goes around at about 1,000 miles an hour, and then, we go around the sun at about 67,000 miles an hour in our orbit. The sun's going around the galaxy about 500,000 miles an hour around the galaxy. The galaxy is going towards a galactic cluster at more than 1,000,000 miles an hour. But, how fast are we going, really? And the only thing you can measure is how fast are you going relative to something else. There's no answer. How fast am I going? Well, I mean, am I still, or am I actually traveling close to the speed of light right now? I don't know. So Einstein said the only way he could really think about how that would work is if the universe was just one big thing. All of time and space exists in a big whole thing. There's only one now. Einstein famously said, the past, present, and future are, persistently annoying illusions. Now, again, do we know this to be true? At the moment, we don't have any better physics, and I doubt the physics will get any less weird than that. But that's sort of the way modern physics thinks the universe may be, is a big whole thing that started from beginning to end and is all now-ish.
But if that's the case, so subjectively we can measure things. We can measure time. But what are we measuring? If it's, are we making artificial time constraints? Are we doing it ourselves? When we create a clock, we create a watch, and the watch is 24 hours a day. It's running. What is it measuring? Yeah, right.
That is exactly the question Albert Einstein asked. That is a deep, excellent question. And so that was the problem. I mean, in a famous thought experiment, Einstein made a clock by setting up two mirrors and having light bounce between the two mirrors. And that was the tick of the clock. Tick, 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 tick. And the problem was that, that's how he started thinking about the speed of light, is that if you had this thing in a spaceship that was going a huge fraction of the speed of light, then a person standing watching it go by would actually watch the light kind of trace out a pattern like this. Because it's actually ticking between the mirrors, but the mirrors are moving along. And so you see the light make this sort of bouncy movement. And that means it's actually traveled farther than the person on the ground who thinks that the mirrors are just sort of, the light is making just a straight up and down line from mirror to mirror. That question that you asked is what completely revolutionized physics. Everything fell apart when people said, how do you even measure time? What does it mean to make a clock? What are we measuring?
I still don't understand what we're measuring.
Oh, Lord. Yeah.
I get it. I don't
know if I have an answer for you. I don't think anybody does.
In the following clip, we will discuss one of the most unsettling concepts in physics, quantum entanglement. This phenomenon suggests that two connected particles can instantly respond to one another, even if they are separated by billions of light years. But the implications go far deeper. If the entire universe started from one tiny point during the Big Bang, are we currently entangled with everything in existence, including black holes and distant galaxies?
I hope your listeners, I want people to come along with us.
Oh, they're coming along.
Yeah, I don't want to say things that sound so stupid. They're like, why are they saying this? So please stop me if we need some more background.
This does not sound stupid in any way, shape, or form. But the idea of quantum entanglement, we should explain that to people.
Yeah.
And what it essentially means is that things are entangled, they're connected regardless of the distance.
Yes.
And it could be an immeasurable amount of distance.
Any distance.
Literally the beginning of the universe distance, 13.8 billion light years away distance. You're entangled with that.
Quantum entanglement was something that even Albert Einstein 100 years ago He understood that quantum mechanics was pointing that way, but he really didn't like it. He called it spooky action at a distance. He hated it because he realized that quantum mechanics had this implication that if things could somehow be connected quantum mechanically, you could take them any distance away from each other, and they would somehow be able to respond to each other instantaneously with no time difference. And he didn't think that would ever actually happen. And then back in the mid 1990s, we started to do experiments with atoms, and we found out that it was real. That it can start off pretty simply. You have two atoms that are in an orbit around, so an atom has a nucleus of protons and electrons in the middle. Sorry. An atom has a nucleus of protons and neutrons. The electrons are flying around in orbits around the atom. Two electrons can be in the same orbit only if they're spinning in different directions. They have an angular momentum. It's called spin. And the only way these two electrons can fit in that orbit together is if they're spinning, one is spinning in an upward direction, one's, say, spinning in a downward direction. Hate the broken finger. So if you take these electrons out of the atom, and you can do that, you know that they're in different spins because they had to be in that orbit together. So now you separate them. You can separate them by any distance you want. Can separate them by centimeters in a laboratory. The Chinese have done this up to the space station that they run and back. You could conceivably do it to another galaxy. If you take those electrons and you separate them, you know that they were spinning in opposite directions. So if you take an electric field and you change the spin of one, the other one immediately changes in response.
Regardless of the distance.
Regardless of the distance. And we know this to be true. We've done this. And the amazing thing is the universe is saying these two things are the same quantum mechanical system. They're basically the same object. They're connected to each other. They're entangled together. And it doesn't matter. Space and time don't matter. You separate them in space any distance you want. How does that work? The universe says the space and time between them doesn't matter. They're the same system. To me, that's the real intriguing thing about, could a civilization learn how to harness that? You're not really even having to worry about traveling from one part to another. Did you watch the three-body problem show?
Yes.
So you have these things called sophons, right? And sophons are entangled to this alien civilization, and they can respond instantaneously because they're entangled. Yes, I mean that's fantastic science, and as far as I can tell, that could be theoretically possible. Yeah.
Well, that's what's bonkers, is that we are made out of all this stuff that's entangled.
What's it entangled to? Is it entangled
Right.
to stuff inside a black hole right now? Is it entangled to stuff that is on the other side of the universe from us? If the Big Bang had all of this stuff in a small volume at once, are we entangled to everything in some way? Seriously.
Seriously.
I mean, is a part of me quantum mechanically right now in the Andromeda galaxy? Yeah, actually. That would be the implication. I mean, talk about... I don't think we understand yet what reality is. I really don't. What does it mean? Are we all somehow the same particle, entangled to each other? Are we connected to everything all at once? I mean, that could be where physics is taking us now.
That's bananas. It's very difficult to think about when you think you're a person in Austin, my feet are on the ground.
Yeah.
Here I am touching this desk. I'm going to get my car later and go get something to eat.
No kidding. You got to feed the cat, right?
Yeah, but that's not really what's going on. It's way more complex, way bigger. You were speculating that could be how some super advanced, intelligent life form travels.
It's always been more compelling to me than the idea of taking a spaceship and traveling somewhere.
This seems super crude.
Yeah.
That seems like the idea of making a horse fly.
Yeah. We talked about that movie Interstellar because there were a lot of good teaching moments in that movie for a physicist. The idea that time really does slow down close to a black hole. And again, we observe this. When we observe things orbiting close to a black hole, you can tell that happens. And the idea that this advanced civilization that we never actually see in the movie somehow communicates through basically space and time itself, through gravity. That's how Matthew McConaughey is able to even go back, in time and space to help his daughter solve, gravity and all that. I wonder if that's really more what it'd be like. Advanced civilizations. I mean, you got to think, right? I mean, you look around the Earth and there are, things like grasshoppers and hamsters that are fantastic, incredibly complex beings. But I mean, you try to teach them quantum mechanics or ask them to, crochet a blanket or whatever, they don't have the capacity. And you've got to think that there's the similar jump where, I mean, we don't even know the right questions to ask that sort of a civilization. I mean, can they see the universe as a whole thing? Do they know that they're connected to everything? And can they somehow use that to travel? Maybe.